Good morning, everybody. Yes, today we're going to do a couple of sections, but they deal with logarithms. Yesterday, the last section, we talked about exponential functions, and we saw how they look. We said an exponential function looks like this. And it's where the exponent is the variable. And the base is some constant. It's variable, it's an exponent. That's why it's called an exponential function. And then we saw if A is bigger than 1, it's an increasing function. It looks like this. It always crosses through 1 because anything to the 0 power is 1. Remember, an x or a function, when x is 0, a to the 0 is 1. And when x is negative, that means the number gets smaller. When x is positive, it gets bigger and bigger and bigger. So this is, let's say, 2 to the power x. When x is 1, y is 2. When x is 2, y is 4. And so on and so forth. So the larger a becomes, the faster it grows. This is something like 5 to the power. And the smaller it goes, let's say it's just 1.5 to the power x. And then if a is between 0 and 1, again, crosses through 1, but this time it's a decreasing function. A has to be greater than 0. And a cannot equal 1. Because 1 to anything is 1, so it'll just be a horizontal line. So that's an exponential function. And remember yesterday we talked about the inverse functions and how inverse functions are symmetrical about the line y equals x. By symmetric, I mean reflexive. So this is the line y equals x. If we had a curve here that looks like that, then we'd have the mirror image of the curve that looks like this, where this would be our function and this would be our inverse. Remember, you switch x and y to find. Okay, so that's leading to where we are today in logarithmic functions. Logarithmic functions are the inverse of exponential functions. logarithmic functions are the inverse of exponential functions. And by that, so if f of x equals a to the power x, then the inverse would look like this. And this is read the log base a of x. That's how you would read that. The log base a of x. So this is your base. It's the same base as the exponential function. And the x's go there. All right, so that's what how the logarithm functions and the exponential functions are related. Let's look at the first example. Example 1. Graph the function y equals, x equals 2y. So because y is an exponent, we have to get it down. Logarithms are used to get the exponent down. So we want to get this, we can't solve it as long as it's an exponent, so we have to get that down. So that's where we use logarithms. To find the inverse function of f of x equals 2x, here are the steps. Because it's the inverse, switch x and y. So we have y is equal to 2x. So first step is switch x and y. Actually, the first step is f of x equals y. So make that change there first. Then switch x and y. Then solve for y. Now, what does that mean? What we're looking for here is this. We're looking for what power do we raise 2 to get x. So here we're trying to get y by itself now. How do we do that? Well, once we figure that out, and I'm gonna show you the formula in a second. Remember, since we solve for y, switch y to the inverse function. So we got to switch y back to f inverse, and that's what we're finding. So that is the procedure that we're going to try to do. Now we got to put it all together. And like I said up there earlier, if f of x equaled 2x, then the inverse, since that's the base, remember the inverse of an exponential is the log. There's the base, and there's my x. So the graph of this, we know the graph of this one is the 2x function. It crosses 1. And because it's got to be symmetric about the line y equals x, the logarithmic function instead of crossing the y value at 1, it crosses the x at 1. And there's that line y equals x. So all the y values become x's and all the x values become y. So that's that example. There's the graph. This is the graph of y equals 2x. This is the graph of the inverse, which is log base 2 of x. All right, so now we're going to start using these values. So as the instruction said, we're looking for what power do we raise the base to equal x. Example 2. Find the following. Log base 10 of 10,000. So there's the base. So now what does the exponent have to be to make it equal 10,000? We have 1, 2, 3, 4. So that's the conversion. So the base, log base 10 of 10,000 is converted to 10 to the power 4th. Because 10 to the power 4th is 10,000. B, log base 10 . So what does 10 have to be raised to equal 0.01? So we know that 10, it tells us each step. So it's -1, -2. So 10 to the power -2. So this whole answer here is log base 10 of 0 equals -2. Log base 10 of 10,000 equals 4. because that's what we're looking for. C. Log base 2 of 8. So we have to figure out what does this equal? What does 2 have to be raised to equal 8? 8 is 2 times 2 times 2, which is 2 to the third. So this equals 3. D. Log base 9 of 3 equals x. So what does the base have to be raised to equal 3? Well, we know that the square root of 9 equals 3. And converting this to exponential, so this equals 1/2. Because 9 to the power 1/2 equals 3. Log base 6 of 1 equals x. So what does 6 have to be raised to equal 1? Only thing, any number raised to 0 equals 1. So x is equal to 0. And we're going to see this is actually is a property. The log base anything of 1 is 0. Log base 8 of 8 equals some number x. What power does 8 have to be raised to equal 8? Since the bases are the same, that means the exponents have to be the same. So x is equal to 1. Right, and these two are actually properties that we're going to spend a lot of time looking at. So those are first two rules. The first two rules was, and we're going to summarize all these in the next section. Log base anything of 1 equals 0. And log base anything of itself is equal to 1. Those are the first two rules. So those were all pretty easy. What about if it's not that simple? How would we figure out the conversion if it wasn't that straightforward? The conversion rule for exponential and logarithmic functions. It's pretty straightforward. We have any log base a of x the conversion, because what we know so far is this. Log base A of X is equal to, let's say, Y. So the conversion is, since this is the base, A is the base, it comes over here and is the base of the answer. Since the base is gone, the log drops off. And there's that conversion. So what this equals is A to the Y is equal to X. So this is the conversion. Whatever the base is, pushes up the answer, and the log drops off. And we can go backwards also. Since this is the base, it's log base A, and you switch X and Y, like we did earlier when we converted to find the inverse. Remember, these are inverses. This is the f of X. This is the inverse. And vice versa, actually. Example 3. Convert. We have 16 equals 2 to the power X. So the conversion, we're going from exponential to logarithmic now. So it's log, here's the base. And we switch these two. So now it's log base 2 of 16 is equal to X. That's the base. Switch those two. And this is we're gonna see that X is 4. But we'll go over that later. B, 10 to the power negative 3 equals 0.001. Converting that to logarithm. This is the base. So it's log base 10. And you switch these two. Log base 10 of 0.001 is equal to negative 3. E to the power t is equal to 70. So it's log base e, switch those, of 70 equals t. Yeah, it follows from here. So here's a, so it becomes the base, and x and y switch. So the answer goes in the question, and the exponent becomes the answer. In a little bit, these are the 3 types of logarithms that we'll have. They have special names to them. And we'll define that in a little bit. Example 4, another conversion. A, let's convert this one. This one is log base 2 of 32 equals 5. So convert it from logarithm to exponential. So the base has to say the base. The base comes over here and pushes up the answer. 2 to the power 5 is equal to 32. Log base A of Q is equal to 8. Again, the base comes over here and pushes up the answer. So it's A to the power 8 is equal to the Q. X equals log base T of M. The base remains the base. It pushes up the answer. So it's T to the power X, and the log drops off. So we're left with M. The next three questions are kind of ridiculous, but we got to use them. So we have to, the next three questions is using a calculator. Find the following. This is example 4 or example 5. So the first one is log 645,778. B is log 0.0000239 equals. And then C, log of -3. And notice these don't have any bases. And that's going to come up when we talk about what that means. So let's look at the calculator. Make sure we're on scientific. And if you notice here that here you have 10 to the power X, you have log, no base, and we have ln. These are there for a specific reason, which we'll talk about shortly. So that's, if we just hit log first, we can't do that. So what we have to do here first is put it on a number 645,778, and we take the log of that. So the answer is 5.81008. Round to 4 decimals. So round to 4 decimals. 1, 2, 3, 4. Since we want 4 decimals, we look at the 5th number. To round, go to the next number and if that number, if it is between 5 and 9, add 1 to the last digit. If it is less than 5, so if it's 0 to 4, then just drop the rounding number. So what this means is this: since we're rounding up to 4 decimal places, we go to the 5th location. That's the one we're looking at. That's the next number. Since this number is between 5 and 9, we add 1 to that number. So that's our answer. If this number was between 0 and 4, then we just drop that number and leave that one alone. And those are your 4 decimal places, because the question asks round to 4 decimal places. All right, let's look at the next one. So we clear that out. And we go to 0.1234239. And we take the log of it. It's going to be negative 4.621602. Again, we're rounding to 4 decimal places. 1, 2, 3, 4. So we look at the 5th. Since that number is between 0 and 4, we just drop all that. And that's our answer. So that's what the whole rounding thing is if this one said only want 2 decimal places, then we look at the first 2 decimal, and then since that one is between 0 and 1, we just drop it off. Let's look at both of these answers before we go to the next one. This is what the x value is right here. Because remember, we're taking log of x equals y. We talked about earlier, the exponential graph is that's e to the power x. And its inverse is the logarithmic function. And it crosses at 1. This one crosses at 1. So when x is bigger than 1, the answer is positive. Sure enough, that's the first one tells us. If x is between 0 and 1, the answer is going to be negative. So looking at that, here's my x value. If I put negative 3 in there, it's not in my domain. This one does not exist because we cannot use 0 or we cannot use negative in there. Because actually it says x has to be strictly greater than 0 for our domain for logarithms. So that one's going to be, actually the computers are going to say error. What it means is the answer doesn't exist because it's not a domain. Let's see. Where's the change of sign? There's invalid input error because we cannot have x's being a 0 or negative. All right. Any questions so far? Pretty straightforward. Let's look at example 6. Are you still reading? I'll hold it. You got this. Example 6. Actually, before we do example 6, let's define the different types of logs that we have. We have the type of logarithm depends on the base. The type of log depends on the base. There are 3 types. We have base 10, base E, and any other base. This is important because remember when we do the conversion to exponentials, we have to know what the bases are. So if it's base 10, if we had a log base 10 of x, we would write that as log x. Notice, if there's no base, it's automatically a 10. That's called a common log. Can you guess why? What's so important about number 10? Perfect. That's our base system. We have a base 10 system. There are 10 numbers. So that's why they call it common log. If it's a base 10, it's a common log. If it's base E, remember, E is that constant number, the 2.7181859. So if it's log base E, then we'll write LNE. Remember, on our calculator, we have log and we have ln. So this one's log base what? Automatically base n. This one's log base E. So yeah, so we know what the calculation is going to be already now. And the reason calculators, all computers use that is standard. Any other base, we have to convert it. And I'll show you that in a second. If it's log base E, the ln, we call that a natural log. And any other base, that base number has to be there. 10, 4, E. All right. So that'll bring us to this example 6. Find each of the following on a calculator. Six, four, five, 7, 7, 8. B is ln of 0.0000239. C is the ln of -5. D is ln of E. And ln1. Three of these we can do without calculators. Which three? Yeah, C, D, and E. Remember, what is this one? This one is very good. Log base E of E is 1. Because if the base and the term are the same, then it's 1. Why is that true? Beautiful. Perfect. Because anything raised to the power 1 is itself. I couldn't have said it better. How about this one? Because yes, anything raised to the power 0 is 1. I knew you had it. What about this one? Very good. Why? Can't be negative because that's not in our domain. So these other two, we just have to get the calculator out, plug in the numbers 6, 4, 5, 7, 7, 8, and take the ln of it. Thirteen, 3, 7, 8, 2, 1, 1, 0, 7. The question says round it to 4 decimal places. So what's my final answer? Yeah, because the 5th number is 1, so we just drop those. Oop. Yeah, so since here's the 4 digits we want, the 5th is a 1, so we just drop it. And then the last one is 0.1234, 39 ln -10.641632. 1, 2, 3, 4. So do we drop the last ones or keep or raise it? Right, because the 5th one is 3, so just drop it. And I should have asked you, what was the sign going to be? How do we know the answer is going to be negative? look at this number here. It's between 0 and 1. Remember the graph of the logarithm? This is the log function. Base anything really. If it's between 0 and 1, the answer is going to be negative. If it's greater than 1, it's going to be positive. Actually, I'm glad you guys are here. That way, if you had any questions, you just ask me straight up. The police came in earlier because they were going to use the room and the light was off. They turned the light on and they freaked. Because the light was not, I was totally pitch darkening. I was just working on my computer. Let's look at example 7. Find log base 5 of 8. So if we go back to the calculator, is this going to help us much? No, because this is log base 10. How do we fix that? To solve logarithmic problems with base other than 10 or e, we need to use the change of base formula. Because we can't have 5. So the change of base formula looks like this. It could be either one of these. There's 2 actual formulas. Because it's the ratio that matters. We can either use ln or we can use log base 10. The answer goes up on top and the base goes on the bottom. This is the change of base formula. Because it's the ratio that's important. And what this one says is, example 7 says, find this equation, find the solution using common logarithms. So how would we write that? Perfect. That's it. Because this is the common log, this is the natural log. So the way we do it in our calculator, put a there's the parenthesis. First one is ln or log of 8, close parenthesis, divided by open parenthesis log of 5. And that's the answer. 1.29202.967. It didn't say how many decimal places we want. So if it was just 4 like all the other ones, since that's a 2, just drop those. The same equation using natural logs. So it would look like natural logs are what? Is it ln or log? Ln. Yeah, so it's ln 8 over ln 5. Eight ln divided by 5 ln. Same thing. Because it's the ratio that's important. It's since the fraction is the same numbers, it'll give us proportionally the same answer. Graphing logs. Example 9. Graph this function. So what do you think it's going to look like? Okay, yeah, because exponentials and logarithmic are both positive increasing functions. Where is the intercept? The logs always cross at 1 on the x-axis. The exponentials cross at 1 on the y-axis. So it'll cross through 1, it'll have this basic shape. y equals log. Is it gonna let me do won't let me do a subscript. Well, that's phooey. Oh well. Well, then we can use a calculator. Well, I'll show you something. Because remember, log, the first one we did was log base 2. That was like that. What do you think happens if we have a log base 5? We know they both cross at 1. So what happens if x is 5? This one, it'll cross at 1 because if x is 5, log base 5 of 5 equals 1. If it's 5, log base 2 of 5 is what? 2 to what power equals 5? 2 to what power equals 4? 2. Yeah, so if it was 4 here instead of 5, then it would be 2. Then this graph would look like this. So the bigger the exponent, the more shallow it becomes. Because it has to grow further out to get where it's going. So that's the graph of that one. How about example 10? F of x equals ln of x. Is this one going to be higher or lower than this one? Yes. Because this one is log base e, which is 2.28. So yeah, this one would look something like this. Now let's look at transformations. Let's look at transformations. Example 11. F of x is equal to ln x plus 3. B, f of x equals 3 minus 1/2 ln x. And C, f of x equals absolute value of ln x minus 1 absolute value. What does this one look like? Because we know the original graph crosses there. It looks like this. That's ln x. What's going to happen to this one? Very good. Exactly. So what this is going to shift to is this. So my origin shifts 3 to the left. So there's my new origin. And the graph, it intercepts 1 to the right. So this is the x-intercept, and the graph looks like this. So the origin shifts from there to there. And so my x-intercept shifts from 1 to -2. All right, the next one is going to require some thinking. Let's do this one step by step. So the original function is ln x. Looks like that. What does the 1/2 in front do? No, not the negative. We do piece by piece. What does the 1/2 do? Shrinks it. So now it's half the size. Now, how does that negative in front of the 1/2? How does that affect it? Flips it where? Yeah, because if x changed from positive x to negative x, then it's flipping. This one changes this whole value, which is y, from positive y to negative y. So it flips it across the x-axis. And then what's the last transformation? No, we're doing this. We're still doing this one. We haven't finished this one yet. We did ln x. That's this one. We did 1/2. We did minus. What about the 3? Where? Mm-hmm. So the horizontal axis shifts up 3 spaces. So there's my new. So there's 1. The origin shifts to there. My x-intercept. So the graph looks like that. Okay, we'll do look at the C one here. The absolute value of ln x minus 1. So the first thing is do it piece by piece. It's an ln function. We know the graph of that one looks like this. What does my horizontal shift do? Yes, right one. So it shifts to the right one. So my My new is shift from here to here. So what does the absolute value of this function do? Here's my fake one. Absolute values make all negatives into positives. So all these are positive, so they stay there. These negatives now flip. Instead of going down here, they now go up. So the only thing that changes is where it's negative. It changes from negative to positive. And since it approaches this vertical asymptote, when I flip this part up, it still has to follow the same shape. So that's what that looks like. You're still looking at it?
Oh,
No, because those are, once you see them, they click. But just initially see them, because originally you'll think you'll flip the whole thing. It's only whatever's negative, that's all absolute values change, negatives, positives. The application problems. In a study by psychologists Bornstein and Bornstein, it was found that the average walking speed, W, in feet per second of a person living in a city of population P was given by this formula, where W is the speed of walking, P is a population. If the population is 106,954, what's the average walking speed? Just plug it in there. Just take this number, plug it in there, take the ln of it, multiply by that, and add that. Do the same thing with that one. So it's not much there. And same thing with the earthquake, the Richter scale. Your initial value and the earthquake value. So those are just plug and play. Right, that's that section.